Okay, so today we're going to take a look at problems involving elevators. Now, I'm sure you've been on an elevator at some point in time, and if you've ever been on one of those like super crazy like fast elevators that take you up to like the top of a really tall building, like the Space Needle type idea, you might notice that there's sometimes in the elevator where it feels like your bottom is dropped out of your stomach, where you and there's other times where it feels like the elevator is falling out from underneath your feet. Well, all of those different experiences come from the relationship of normal force and the gravitational force. So we're going to look at an example of an elevator where we have kind of this elevator shaft, like with the elevator inside the building. It's held by some sort of cable. We don't really care what forces are causing the elevator to move. And then actually we are going to have a person standing on a scale inside of the elevator. So to understand what's going on with this scale, the scale is what allows us to measure weight, the force due to gravity. And it does that actually by measuring the normal force exerted on it. Because if I was to take a look at that scale, what happens is if I'm standing on top of the scale, if I looked at the forces acting on the scale, I would have a gravitational force of the Earth on the scale. The scale is sitting on the floor of the elevator. So I would have the force of the normal force of the elevator on the scale. And then I would also have my force pushing down. Now my force pushing down is a normal force. The normal force of me on the scale. Now, I just picked an arbitrary length for my normal force here, my elevator scale, but I find that that value is wrong because the normal force of the elevator on the scale would have to balance out these two forces. But I don't really care about that because what happens is when you place the scale without anyone standing on it, it basically takes care of the force of gravity and the normal force due to the Earth. And that process happens, you know, when you it's called tearing. But basically it balances itself out so you don't put anything on the scale at first. And then with Earth on the scale and just the normal force of the elevator on the scale, that those are equal. And so whatever force is being experienced by the sensors in this scale, it determines that amount of force to equal 0. So it zeroes out that value. You could have something sitting on it, like when in chemistry you might have done this with like a tray that you were going to pour something into. You put the tray on there, you hit tear, and it zeroes it out, and then it ignores that as well. So that's what happens when you get on the elevator, is we are assuming here that it's already been zeroed out, that the force of the Earth on the scale and the normal force of the elevator on the scale themselves are taken care of. So then all that's going to be measured by this scale is essentially the normal force of me on the scale. That is going to be what the scale reads. So the scale doesn't read our weight. The scale reads the normal force of me pushing on the scale. Now think of Newton's third law. If I were to look at the forces acting on me, well, the forces acting on me are going to be a force of gravity of the Earth on me. And I will have the normal force of me on the scale on me. Sorry, the scale on me. The scale on me. Those are the two forces that'll be acting on me in the elevator. So when I'm just standing on the elevator and the elevator's at rest, those are the forces. So what I'm assuming is that the scale reading, which is reading So the scale reads the normal force of me on the scale. I'm assuming, due to Newton's third law, that that is equal in magnitude to the normal force of the scale on me, which I am then assuming is equal to the force of gravity of the earth on me, which is the same thing as weight. So I'm assuming that the scale is reading my weight, but there's all of these steps in between. So if I'm standing at rest on the scale and it's horizontal and so forth, then yes, the scale is going to read my weight, or its best estimate of my weight. Well, but remember that normal force is actually very variable. I don't know if you've ever done this or tried to make the reading on your bathroom scale read a different number than when you stand on it, like either by pressing down to make it go up, or maybe lifting up, like putting some of your weight on like the counter so it lifts it up so it makes it smaller. It's actually fun to play with the scale. For example, put it on a ramp and stand on the scale and see what happens. So the scale doesn't actually read our weight. The scale, we assume, is giving us our apparent weight. And we are hoping that our weight is equal to our apparent weight when we step on a bathroom scale. So that's kind of our setup here. Now let's look at elevators. So let's assume, first of all, that our elevator is moving upwards at a constant speed. If I wanted to look at the forces that are acting on me, I'm going to have the force of gravity, and I am going to have the normal force. Now remember, the scale reads the normal force, which I'm assuming is equal to the normal force on the scale and so forth and all that. So I'm not going to put all those subscripts in here over and over and over again. I'm just going to assume that the scale is equal to, the scale reading is equal to my normal force. And so in this case, if I were to write a net force equation, in the y direction, my net force is equal to my normal force minus the force of gravity. And because I'm moving at a constant speed, I have no acceleration, so that's equal to 0. So my normal force would equal the force of gravity. So that tells me that my scale would read my weight, which is my force of gravity. So it would give me my actual weight. Well, what if I'm moving upwards, but I'm not moving at a constant speed? What if I'm moving upwards and I'm getting faster? Okay, well, if I'm moving upwards and getting faster, that means I have an acceleration. Now, if I'm getting faster, my velocity and my acceleration have to be in the same direction. So that's telling me that my acceleration is in the upwards direction. If my acceleration is in the upwards direction, that tells me that my net force must also be in the upward direction. So that means that my normal force and my gravitational force cannot be equal. I've not added any forces. I'm still just standing on the scale. The elevator itself experiences other forces in order for it to accelerate, a change in its forces, but there isn't really any change in the types of forces that are acting on me just because the elevator is accelerating. So how do I make my net force larger? Well, my gravitational force is a constant because it's equal to m times g, and I'm assuming this isn't some space elevator that's accelerating me up to, all the way up to the ISS. So g is a constant. My mass doesn't change by the elevator starting to move. So therefore, my force of gravity is constant. Which means if I have a net force, it's not because my force of gravity changed. It's because my normal force changed. Basically, by the elevator getting moved upwards by its cable at a faster and faster rate, it's almost like the elevator is slamming up into me. So therefore, I'm getting a larger normal force acting on me. So in this case, if I was to write a net force equation, my net force equation would still be my normal force minus my gravitational force, but instead of equaling 0, this is going to equal m times a. So my normal force is what the scale reads, so it's going to equal Fg plus ma. So it's going to equal mg plus ma. So it's going to be m times g plus a. So this is what the scale reads. So the scale is going to read a value greater than my weight. So my apparent weight will be larger than my actual weight. And it's going to be larger essentially by the amount of mass times acceleration I have. So it's going to be larger by that amount. So as my elevator is moving upwards and getting faster, my normal force is increasing. And as my acceleration gets larger and larger and larger, the faster and faster and faster and faster and faster, the bigger the rate of change of that velocity, the bigger my normal force is going to be, and the more it's going to feel like that elevator is slamming up into me, giving me a feeling of bigger weight. So that's kind of what happens when the elevator is getting faster. Well, what if I was moving upwards, but I was slowing down? Well, if I'm upwards and slowing down, if a slowing means my velocity and acceleration are in opposite directions. So this means that my acceleration is actually in the downwards direction. So once again, my force of gravity is constant. It can't change. So if I have a downwards acceleration, I have a downwards net force, which means my gravitational force must now be larger than my normal force. Well, my gravitational force doesn't change, so that means my normal force has to get smaller. So in this case, my gravitational force is larger than my normal force. My normal force is my apparent weight. So that's what the scale reads. So my apparent weight is going to be smaller than my gravitational force. And this is where you get the feeling of weightlessness, the feeling like the floor has fallen out from beneath you. Because what happens is the elevator gets kind of accelerated downwards. Now it's actually slowing down, but you're still moving up at the speed you were. The elevator is getting slowed down underneath you. So it's almost like you're coming up off of the surface of the elevator. And actually, if it's slammed on the brakes and the elevator could stop instantly, you would still keep moving up with your with your momentum, and you would hit the ceiling of the elevator, and you would feel weightless in there, because the feeling of weightlessness comes from when your normal force is equal to 0, because that means your apparent weight, your feeling of weight, is equal to 0. So if you've ever been on a roller coaster and you feel weightless, it usually is going to happen somewhere like on the top of an inside loop, where basically it feels like you're falling out from the cart because you're losing contact with the seat. So it feels like you're weightless. You're not actually weightless. Your weight hasn't changed. Your mass times the acceleration due to gravity is still going to be a constant in those situations. So we looked at a couple situations here with elevators. There are other situations. So for example, we could moving down at a constant speed. We could be moving down and speeding up. We could moving down and slowing down. And you're going to go through the same process to analyze it. And you'll get a chance to practice that on your assignments in class. So these elevator problems come into play a lot. So just kind of keep in mind that it's the normal force that is always changing. Your gravitational force is constant. And your feeling of weight comes from that normal force, and we assume that our scale is always reading our normal force. All right, have a good day.